Okay. So we've been talking about calculating equilibrium constant K, and that can help us figure out a number of different things. So what the equilibrium constant K allows us to do is figure out the tendency for a reaction to occur. If we have a large value of K, that means that it's going to be a product-favored reaction. Recall that. K greater than 1. This favors the forward direction, favors products, that kind of thing. If K is less than 1, it favors the reverse reaction, or it means it's reactant favored. So it's reactants will be the main components if K is less than 1. The other thing that K will inform us of is the concentrations at which equilibrium will occur given initial concentrations. So that's all the ice table stuff we've just been doing. Okay. The other thing that's useful, and that's what we're moving on to next, is our given set of concentrations, the equilibrium concentrations. So we've let a reaction happen, we draw a sample from the vessel, we figure out the concentrations of each of the species present, and we want to know, is the reaction at equilibrium? Well, the thing that we can do is calculate what's called the reaction quotient, which is the exact same calculation as K, it just has a slightly different definition. The other thing that we can do is if the reaction is not at equilibrium, we can figure out if more reactants are going to form to get us to equilibrium or more products are going to form. Okay. So the reaction quotient is basically the same calculation as K. It's just what we use if we want to figure out if a reaction is at equilibrium, or if we know it's not at equilibrium, which direction the reaction needs to proceed to reach equilibrium. So if we write out Q for our general reaction A plus B in equilibrium with D plus E, we'll get Q is equal to the concentration of D raised to its coefficient times the concentration of E raised to its coefficient divided by the concentration of A raised to its coefficient times the concentration of B raised to its coefficient. So you can see that's the exact same thing as K. The only difference is in how we define it. So with Q, we're saying is this at equilibrium, or this is not at equilibrium, therefore we need to figure out which direction the reaction needs to go. We'll do some examples. What we will find, though, we're often going to be comparing Q to the value of K. So we're going to calculate Q, we're going to compare it to K, and if Q is equal to K, that tells us that the system is at equilibrium, or the reaction's at equilibrium. If Q is less than K, that means that we have more reactants than products, and so the reaction is going to proceed towards the products. If Q is greater than K, we have more products than reactants, and the reaction proceeds in the reverse direction back towards the reactants. And so mathematically, if you're looking at this, when there are more reactants than products, the number on the denominator gets greater. And so that makes Q, what, smaller or larger? If this is large, that makes this small, right? Yeah. And okay, so we're going to say that means that Q is less than K, right? So then if we have more products, larger value in the numerator than at equilibrium, Q is going to be greater than K. We have to form more reactants to get back to equilibrium. Back here, if Q is greater than K, we have more products than reactants. And so let's do a calculation, and then we're going to look at how this plays out sort of graphically. Okay, so we'll go back to our ammonia example. We have our N2 plus 3H2 in equilibrium with NH3. And at this temperature, whatever we're at, K is equal to 6 times 10 to the minus 2. At some point during the formation of the ammonia, we take a sample and we find these concentrations. Concentration of N2 is 1 times 10 to the minus 5, H2, 2 times 10 to the minus 3, and NH3 is 1 times 10 to the minus 3. And so we want to know, is the reaction at equilibrium? So to find that, we need to calculate Q. And so we write Q just the same way as we would K. So Q, missing a coefficient here, aren't I? There should be a 2 there. I might have a math error in my notes now, just so we know. Okay, so Q is equal to 1 times 10 to the minus 3 squared over concentration of N2, that's 1 times 10 to the minus 5, times the concentration of H2 cubed, 2 times 10 to the minus 3 cubed. So let's calculate that. Check my math here. 1.25 times 10 to the 7th. You got that? Okay. Cool. I'll assume we've done it correctly. Okay. So we've calculated Q. We still don't know if the reaction is at equilibrium until we compare the value of Q that we calculate to that of K. K for this reaction at this temperature is 6 times 10 to the minus 2. And so we can see that Q is much greater than K. Right? What are those called? They're not carats. These meaning much, much greater. Okay, so the reverse reaction has to occur. All right? So that means the reaction needs to proceed towards the reactants. Okay. So mathematically, does that make sense? If we have a large value of K, a large value of Q in comparison to K, we must have a larger numerator and a smaller denominator in some way, right, than what we calculated for K. And so in order to balance that out, to go more towards this value, right, we need to decrease this value and increase these denominator values, right, which means less products, more reactants. So the reaction needs to go towards the reactants. Make sense? Okay. Okay, so let's take a look now. We're going to use our sphere model. Interesting. So we can say that we have the reaction A2 plus B2 in equilibrium with 2A. This is slightly different than the other reaction with the spheres. But in any case, A is red, B is blue. And we can say that each sphere represents each molecule represents 1 mole per liter. So we have in our box here 1, 2, 3, 4, 5, 6 of AB, 1 of B2, and 1 of A2. So what happens to the mixture? This is basically saying, is this reaction at equilibrium? If it's not, does it go towards the reactants or does it go towards the products? Or is it actually at equilibrium? We have a K value for this reaction, 1.5. So let's go ahead, calculate Q for this reaction. So if we're looking at Q, Q is going to be equal to the concentration of AB squared over the concentration of A2 times the concentration of B2. And just using our loosely defined concentrations here, we have 6 squared over 1 times 1, right? So we end up with 36 for Q. So what happens to the mixture? Go towards the reactants, yep. Too much products, for instance, so the reaction needs to proceed towards the reactant side. Did I say that backwards? Too much products needs to proceed towards the reactants in order to reach equilibrium. Questions on that? Or the previous slide? Okay. So essentially what we're doing is thinking about the way that affecting the concentration of a reaction affects the outcome of the reaction. This is, when we make a change to a reaction, there are a number of different things we can change, and how those changes affect the equilibrium. This is referred to as Le Chatelier's principle. So specifically looking at the effect of concentration of equilibrium, just for this reaction, which I still haven't written correctly. There we go. We can think about increasing the concentration of product. In this case, increasing the ammonia concentration. If we do that, only affect the ammonia concentration. We have a vessel that has N2H2 and NH3 in it. We add more NH3. That has to push the reaction towards the reactants. And so Q becomes greater than K, shifts to the reactants, and we form more reactants, more N2, more H2. If we increase the concentration of one of the reactants, say we add more N2, we haven't affected anything else, just adding more N2. Now we've got additional reactant. If we calculate Q, it's going to be less than K, and the reaction shifts towards the products, and more ammonia is formed. Okay. Now we can affect any of the reactants and products, increase, decrease their concentrations, and we should be able to predict how that affects the equilibrium. So if we somehow remove ammonia from the system, that's going to drive the reaction forward. So we're going to produce more ammonia. If we increase the amount of H2, okay, the other reactant we haven't talked about yet, if we increase that concentration, it drives the reaction forward, we produce more products. If we decrease any of the reactants, that's going to force the reaction back to the reactant side to regain that equilibrium. Okay? So if we look at this in terms of a figure, I like this figure. We're going to look at this in a couple ways. So these are concentrations of ammonia, nitrogen, and hydrogen. And so we've got equilibrium established. Is what. Did I run out of juice? Yep. Well, this is going to be interesting. All right, so we've got an equilibrium established. We have a constant concentration of N2, NH3, and H2. If we add H2, we see this sharp rise in concentration. So we're adding a reactant, okay? Sharp rise. Notice what happens to the other concentrations, right? After some time, we see a decrease in the H2 concentration, we see a decrease in the N2 concentration, and the ammonia concentration increases. And eventually, we reestablish equilibrium. But the ammonia concentration is higher than it once was. Okay? So we've effectively made a way to produce more ammonia during this reaction by adding more reactant. That makes sense. The N2 concentration decreases relative to where it was initially. We had more H2 it could react with, so that goes away, decreases in concentration. The H2 concentration, because we added so much of it, its equilibrium concentration is now higher than it once was, that initial concentration, but it has decreased in order to get there. Okay? So if you were to assign values to H2, NH3, and N2 in terms of their concentrations and calculate Q here versus here, you would end up with the same value, even though you're putting in different numbers. Okay? And that's because we have equilibrium. So we've achieved equilibrium by saying that Q is equal to K for this reaction for this particular temperature. So again, we can do the thing where we affect the concentrations. We remove some of the ammonia, and we see a sharp decrease in the ammonia concentration, but then it increases somewhat. Okay? And the N2 concentration decreases, the H2 concentration decreases. So we've effectively made another way to form more ammonia. Now, what it looks like here, if you think about this, so here you have an initial concentration of ammonia. This concentration, this one that's regained, is lower, right? But I just said that we've made more ammonia. So you have to count the amount of ammonia that we've removed from the system. We've collected that, we saved it. Now we just removed that ammonia, we're holding on to it. We figured out a way to add more, to make more ammonia. Does that make sense? Okay. So we can affect the equilibrium by changing concentrations of various species, adding and removing products. We can also do so by changing the pressure. There are three ways that we can change the pressure for a reaction. We can add or remove gaseous products or reactants. We can add an inert gas, or we can change the volume of the container. Okay? If you're imagining just a container where we're measuring the pressure, doing each of these three things, you can imagine the pressure being affected. But let's look at how these are affected in general. Hang on, let me check one also. Okay, so let's say we have a container that has an equilibrium of 2A in equilibrium with B. And A is represented by the red spheres. B is represented by the green spheres. If you have red-green colorblind, I truly apologize. I did not catch this earlier. We'll work on this slide. Okay. Okay, so we have an initial volume. If we decrease the volume, what happens? We increase the pressure. This is PV equals nRT. So if you decrease the volume of the container, you're increasing the pressure. If you increase the volume, you're effectively decreasing the pressure. Okay, so remember how your volumes and your pressures are related. That's PV equals nRT. So I'm going to write this with my finger. It will look bad. Okay. I'm out of battery on my pencil. So if we decrease the volume and increase the pressure, what's going to happen? Are we going to form more products or more reactants? Well, it actually depends on the amount of reactants and products in the gas phase. So if we look at our equilibrium, we have 2A in equilibrium with B. Okay? So if we decrease the volume and increase the pressure, the side with the fewer moles of gas are favored. So if we increase P, side with, so sorry about this, fewer moles gas favored. And so in this example, that's the product side. We have 2 moles of gas on the reactant side. We have 1 mole of gas on the product side. So if we increase the pressure by decreasing the volume, we should form more products. Everyone okay with that? The battery died on my microphone. I've got those though. Wow. What a day. All right, there we go. Okay. Okay, questions on that? Okay, so then, let's see everything. Slide, I think it is, yeah. So here's an example, back to our parable figure with red and green spheres. If we've decreased the volume, increased the pressure, we're going to favor the side. The product side, it has fewer moles of gas. And this sphere does, or this box does represent having more moles of gas, more green spheres. So now if we increase the volume and decrease the pressure, the opposite happens. So the side with more moles of gas is favored. I'm going to try to write more moles favored. And so in this example, that side is the reactant side, and so we should see that more reactants are formed. Okay? And so the figure's sort of showing by relative size of the boxes and by the colors of the spheres what happens when you affect the pressure by changing the volume. Okay, so we have more red spheres on the product side, or on at equilibrium when we've increased the volume and decreased the pressure. Okay. So the other thing we can do is add and remove gaseous product or reactant. That's the same sort of effect that we've talked about with ammonia. Ammonia, that reaction was in the gas phase. This adding and removing reactants and products works for both aqueous species and gaseous species. So it's the same sort of effect. It doesn't matter that it's a gas versus a aqueous thing. So if you remove product, you're going to form more product. If you remove reactant, you're going to form more reactant, and all of that. The one thing, though, that we hadn't talked about yet is adding an inert gas. So when you add an inert gas to a reaction, it does increase the pressure on the vessel, but it does not affect the concentration or the partial pressures of the gases. And so it does not affect the equilibrium. Okay, so this is one of those questions that could show up on an exam. One of those sounds like, how we've increased the pressure by adding an inert gas. What happens to the equilibrium? If you've added an inert gas, it does not affect the equilibrium concentrations. Okay, so keep that one in mind. Questions on changing pressure? Okay. We can also affect, oh yes, sir. An inert gas is going to be any gas that doesn't have any sort of reaction with the equilibrium of interest. And oftentimes an inert gas is going to be like a noble gas. And so it would specifically say add an inert gas, because otherwise you probably wouldn't recognize if there could be a side reaction. Yeah, good question. Anything else? Okay. Okay, so changing temperature. So to determine how a reaction is affected by the temperature, we need to know if a reaction is exothermic or endothermic. And so we're going to be thinking about temperature as heat. If a reaction is exothermic, recall that it gives off heat. What's the sign of delta H on that? It's what? Negative, yep. So we have a negative delta H. If a reaction is endothermic, heat is a reactant, and it's a positive delta H. Okay. So by thinking about heat as a reactant or product, if we can kind of simplify our thinking process, because we know what happens when we add a reactant or a product to our equilibrium. And we've talked about changing the concentrations of our species present at equilibrium, and we can predict what's going to happen. So with the ammonia reaction, if we add NH3, add the product, we know that we're going to form more reactants. So if we can think about heat as a reactant or a product, we know if we add more heat, it's going to drive the reaction one way or another. Okay? Now it's going to get complicated with the writing. So, okay, we have an exothermic reaction, maybe not so bad. Here we have carbon monoxide plus hydrogen gas in equilibrium with methane and water. Delta H for this reaction is minus 206.2 kilojoules. And we can think about it as a product. It's giving off heat, therefore it's a product. And when I work these problems, will actually write plus heat as a product. Okay? That way I can sort of picture what's happening. For our endothermic reaction, here we have, this is our ammonia reaction. Oh, goodness gracious, there's that too again. Because it's endothermic, heat is a reactant. So I add heat plus heat on the reactant side. Okay. I swear that says heat. So for our exothermic reaction, if we increase the temperature, if we increase the heat, which way is the reaction going to go to regain equilibrium? Towards the reactants or towards the products? Yeah. Towards the reactants, right. If we increase heat more, I'm going to do R for reactants formed. And vice versa. If we decrease the heat, we put this reaction on ice, okay? We remove heat from the system, we're going to form more products. Okay? That make sense? If we decrease the temperature, we form more products. Opposite is true for an endothermic reaction. If we increase the heat by increasing the temperature, we're adding more reactant, and so the more products are formed. If we remove heat by decreasing the temperature, we get more reactants formed. Okay. Questions on that? Okay. Let's ignore this part for right now. For the reaction of I2 plus Br2 in equilibrium with 2 IBr, we have an equilibrium value of Kc of 280 at 150 degrees Celsius. If we put 0.5 moles of IBr in a 2-liter flask and allow it to reach equilibrium, which way does the reaction proceed, towards the reactants or the products? We're going to ignore that hard part with all the math first. We go towards the reactants or the products? So we're going to go towards the reactant side. So if we just put product in our solution, or in our flask, we have to form reactants in order to gain equilibrium. Okay. Let's imagine we have our empty vessel, and we just put I2 in that vessel. What happens with regard to this equilibrium? Goes towards reactants, products, nothing. If we only have I2, nothing else, nothing's going to happen, right? There's no other reactant. There's no Br2 to react with. So I think you've had a couple of homework questions like this. What if you have I2 and IBr in a flask? That's it, no Br2. Does the reaction happen? Yes, yeah, it does. And you will form more Br2 in order to achieve equilibrium. But yeah, so there are a few questions in your homework like that. I like those questions. They make you think. I think because I don't have a pen, this will be too hard to do. So we are going to pick up here next time. Happy to answer any questions before you all go.